Here's an example of a goodness of fit test. This question says, an investigator analyzed the leading digits from 771 checks issued by 7 suspect companies. The frequencies were found to be 246, 134, 88, 80, 70, 60, 44, 34, and 15. And those digits correspond to the leading digits of 1, 2, 3, 4, 5, 6, 7, 8, and 9 respectively. If the observed frequencies are substantially different from the frequencies expected with Benford's law shown below, the check amounts appear to result from fraud. Use a 0.05 significance level to test for goodness of fit with Benford's law. Does it appear that the checks are the result of fraud? So we are basically going to check that the different categories here, which are the leading digits of the check numbers, 1, 2, 3, 4, 5, etc., and these observed values that we got, are those conforming to Benford's law. Benford's law says that the leading digit of 1 should occur 31.1% of the time. A leading digit of 2 should conform 17.6% of the time. A leading digit of 3 should appear 12.5% of the time, and so on. So are these frequencies that we got actually conforming to that or not? We're going to perform a goodness of fit test to find out. So in a goodness of fit test, the null hypothesis is always that the distribution is agreeing with or fitting to the claimed distribution. So here, the claimed distribution is that of what's called Benford's law. So we would select that, let's see, the leading digits are from a population that conforms to Benford's law. That was our claim, and so in a goodness of fit test, our claim is going in the null hypothesis. So the alternative hypothesis is that that's not true. There's at least one of these categories, at least one of these leading digits that is not conforming with Benford's law. So here we would choose at least one leading digit has a frequency that does not conform to Benford's law. So now we want to calculate the test statistic for this hypothesis test. So to do that, we need to open the data, and we're going to open that in StatCrunch by clicking on the little blue icon in the top corner of the data and selecting Open in StatCrunch. So here's the information. Here's the leading digits. Here's the actual frequencies of those digits, the actual values we observed. Now in this one, the way we were given Benford's law here, these are not actual counts. These are percentages. This is telling us what percent of the total time these different leading digits should occur. So this one is a little bit apples to oranges right now. The observed frequencies we have are actual frequencies. These are actual counts of the numbers of 1s, 2s, 3s, 4s, and so on that we got from our data. But Benford's law is just giving us a percentage. So we don't actually know what the counts should be. We only know what percent of the time this should occur. So what we're going to need to do is do a quick calculation first to figure out what these percentages would calculate to if we wanted them as actual counts instead of percentages. So how do we do that? So remember, a percentage is just out of a total. So 30.1% is like 30.1 out of 100. 30.1 divided by 100 is how we would represent that percent. So what we want to do is we want to figure out how many total observations there were here, and then figure out what 30% of that total would be. So this is how we're going to do that. We're going to go and create a formula by going to Data, Compute, Expression. So the expression that we want, we're going to build right here. So again, what we want to do is we want to take the total number of observations that occurred in the sample that we got. That basically means we would add up all the frequencies for the observed data. We can do that part by doing this. Sum means add, and then in parentheses, we're going to go ahead and put the actual frequency. So double click. So we're going to sum or add up all the numbers in the actual frequency column. That would give us the total number of observations for all the different leading check numbers that we had in our sample. Then what we're going to do is we're going to multiply that total by whatever percentage value there was in the Benford's Law column. So we can click on Benford's Law and it will know to take whatever value appeared in that column. And remember, then we're going to divide it by 100 because those were percentages. So that percent means it's out of 100. So the total of the actual frequencies times the percentage for each one. And we click OK. And if we want to, we can label this column. So these are our expected frequencies. So that's how I'm going to label it. Is our expected frequencies. We already had the expected percentages. These are the actual expected frequencies. Okay. Notice that a new column has been created here with the expected frequencies for each of these leading digits. So now I have two apples to apples things to compare. I have the actual frequencies that were observed in the sample, and then I have the expected frequencies that would have occurred if we were following Benford's Law. So since I now have frequencies that I can compare to frequencies, apples to apples, we can now perform our Goodness of Fit test. To perform a Goodness of Fit test, we're going to go to Stat, Goodness of Fit, and chi-squared test. So the observed, remember, were in the actual frequency column. Those were the actual number of times that we observed the different check leading numbers. And the expected frequencies are in that column we just created that we called expected frequencies. That's it. Now we can click Compute. And we now have the chi-squared value, the test statistic, and the p-value for this test. So the first thing we were asked for was the test statistic. So we can go ahead and just copy this test statistic and paste it over here. This said to round to 3 decimal places, so that's 1, 2, 3. The third decimal place is a 4. The number that comes after it is a 4, which means we round down and we don't change that 4 to a 5. Now we want the p-value. Remember, the p-value was right there in StatCrunch, right next to the test statistic. So we can copy that and paste it over. This one says to round to 4 decimal places, and this already has 4 decimal places after the decimal point, so that's good. So now we need to come to our conclusion. So how do we come to the conclusion? Remember, for any hypothesis test, the way we're going to decide what to do for our conclusion is we're going to compare our p-value to our significance level and ask ourselves which one is bigger. In this case, the p-value is 0.0281 and the significance level is 0.05. So 0.05 is bigger than 0.0281. So in this case, the p-value is smaller, less than the significance level. When the p-value is less than the significance level, we are going to reject H0. We reject our null hypothesis. So the first thing we should do here is choose to reject H0. Now let's think about what that means. Remember, in a Goodness of Fit test, the claim is always in the null hypothesis. So here, the claim was that the frequencies here were going to conform with Benford's Law, and that's what the null hypothesis says. But based on our p-value, we just decided to reject that statement. In other words, I reject the notion that the frequencies here are conforming to Benford's Law. I don't think that's actually happening. I don't have evidence to support that. So here we would say there is not sufficient evidence. So there is sufficient evidence to warrant rejection of the claim that the leading digits are from a population with a distribution that conforms to Benford's Law. So you have to pay very close attention to the wording. You notice I almost made a mistake. There is evidence to warrant rejection, because we have accepted this. In other words, we did not reject it. And finally, it does appear or does not appear that the checks are the result of fraud. Well, we just said that we do not think these conform to Benford's Law, and if you remember up here, it said if the observed frequencies are different from the frequencies expected with Benford's Law, which is what we found, then the checks appear to result from fraud. So since our data here did not appear to conform to Benford's law, based on this information they gave us here, it does appear that the checks are fraudulent. So it does appear that the checks are a result of fraud.